Let's talk about ABG.
ABG.
Arterial blood gases. Let me preface this by saying that you can get the same or close enough out of a venous blood sample, but arterial is the gold standard. So, the lecture objectives here, we're going to talk about the relevance of why you would do this. We're going to do some calculations. We're going to make diagnoses about what pH disturbance we're dealing with using a set number of formulas. We'll work our way through here. If you look on D2L, there are three things that I posted. This lecture plus a chapter from the American Heart Association's Advanced Cardiac Life Support book from about 1985. That's the best explanation of how to interpret ABGs I've ever seen, I've ever read, and that forms the basis of this talk. So if you get lost during this talk, you go back and read that article, and it walks you through and gives you the science behind it. But I'm going to try to simplify it as best I can here. There's also a bunch of sample ABGs for you to work on, come up with some answers at your leisure, and then you can compare it with your classmates to see if you got the same right or wrong answer. So, ABGs, the number one place for obtaining a blood gas, an arterial blood gas, is the radial artery. And you can feel your radial pulse quite nicely. Keep in mind that a lot of times you're going to be getting ABGs during cardiac arrest. So the pulse, the only pulse you feel is the pulse generated by chest compressions. So it's not quite as good as your own pulse right now. You can also try to go for the femoral artery. The femoral artery sits midway along the inguinal ligament between the pubic tubercle and the ASIS. So just feel both of those, pick a point in between, and jab the leg with a needle. That is, if you can't feel the pulse. Again, chest compressions will generate a faint pulse in the femoral artery. Why you would get an ABG? Well, this is a serious procedure. When you do a venipuncture, when you stick a needle in a vein, you can put you can apply pressure on the vein for about 30 seconds and then it stops bleeding. With an ABG, once you stick a hole in an artery, you have to apply pressure for 5 minutes minimum to prevent it from bleeding. Now, keep in mind that if you're running a code and you want an ABG, you just tied up one of your helpers for 5 minutes, putting compression on an artery. So do you really need that ABG? This is something that you should seriously think about. Now, reasons for getting it would be in cardiac arrest. What is the level of acidosis you're getting? What's the pH of this person who's not breathing? Obviously, if you're not breathing, CO2 builds up. As I'll show you in a minute, CO2 turns into carbonic acid, so the pH is going to go down. You don't operate outside of a narrow range of pH. So other examples of when you would get this, it says metabolic diabetic ketoacidosis. How bad is the acidosis? And what do you need to do to correct it? Neural problems would be like head injuries, a coma, unresponsiveness, and then of course cardiac arrest. It's a cheap procedure to do. You're dealing with gases, and pressure of gases dissolve gases in the blood. So once you stick the radial artery, that little syringe there, you see that they're holding the syringe like a dart. So once you stick it in the artery, the pressure of the artery is enough to fill the syringe itself. You don't have to pull back on the plunger, it'll fill itself. Then you take it out and stick it in a little block of gel that blocks the hole. because you don't want the hole of the needle with gas exchange occurring with the outside air. You block it by sticking it in this little block of gelatin, and then you put it on ice, because temperature affects how gas is dissolved in a liquid. So you put it on ice and run it straight to the lab. It has to go straight to the lab within a few minutes, or it's no good. You can't set it aside and run it 2 hours later. It's no good. You have to go straight to the lab. Usually you'll have a runner. So now you tied up two people. You've got somebody putting pressure on the artery and somebody running down to the lab. You're running out of help. So keep in mind, consider that when you decide whether or not to do ABG. Remember Allen's test from anatomy? I wasn't kidding with you. One of the students, what the hell are you doing there? I would have handed it to you. But this is more entertaining. One of the second-year students, he started his clinical year in January in the emergency room, and they were doing ABGs on everybody, and nobody was doing an Allen's test. So he said, shouldn't you be doing an Allen's test? And well, shut up. So anyway, don't forget the Allen's test. You don't want to be the one liable for making somebody's hand gangrenous. All right, so here, you guys remember there are two elements here about oxygen. One of them is its saturation, the hemoglobin saturation. How much oxygen is bound to hemoglobin versus the amount of oxygen molecules, O2 molecules dissolved in blood, not attached to hemoglobin. So you've got oxygen saturation and oxygen pressure. It's oxygen pressure that drives oxygen into the tissues. It's not saturation, it's pressure. That's an important point. You remember the hemoglobin oxygen dissociation curve here. Normally, we've got pressure on this side, measured in millimeters of mercury, PO2, the partial pressure of oxygen, PO2. And on this side over here, it's funny, somebody told me one time, said, why can't you ever just lecture on something like normal? Why you always got to bring this crap down here and confuse everybody, and make it hard? So if that's the way you feel about me, well, sorry. So anyway, on this side over here is saturation. Normally, you have about 90% of your hemoglobin, or actually it's more than 94% of your hemoglobin is saturated at any one time. 94%. So we're up here is the normal, 94 to 99 is the normal hemoglobin saturation. The pressure of that dissolved oxygen is about 80 millimeters of mercury. Around 80 millimeters of mercury normally. So if you look at this curve, if you plot these 2 points, you're up here on the curve. Now, if you start falling off the curve, if you're not breathing, or if there's something, you have pneumonia, or there's something, the asthma, or something is causing a decrease in ventilation and diffusion, you're going to start falling off this curve. Once your oxygen saturation gets to 80%, which is not, you would think that's not very bad. If you, though, follow it over, 80% is now down to 50% in terms of the partial pressure of oxygen, which means your diffusion capacity has gone down substantially. So when you have a kid in with RSV, and they're satting at 90%, that's bad. You would think 90%, hey, that's pretty good, that's an 8. No, it's bad, because they're starting on this slope. So you've got to address that by giving them supplemental oxygen. You want the oxygen, you want their saturation between 94 and 99%. Now, why not 100%? Well, the problem with 100% is that there's no 101%. You can't saturate more than 100% of hemoglobin, right? But if you keep pouring oxygen in there, you can increase the partial pressure on up to hundreds. You're setting it 100%, but the partial pressure might be as high as 500. What did I say happens with oxygen at high levels? Free radical formation, not good. ARDS, IRDS, neurological things happen. One of the things that's interesting that happens, I did this to a patient. I kept, she was a status asthmaticus, and I couldn't get her cleared, and I kept pouring the oxygen to her, and I wound up her, when I got Abg back, it was hundreds. Well, she would stop breathing. And I'm like, oh crap, she's closed off, I gotta intubate her. Well, she stopped breathing because her partial pressure was like 6,000. It wasn't that high, but she didn't have to breathe. She didn't have to breathe for 2 weeks. She had so much oxygen dissolved in her blood, she didn't have to breathe. But her O2 sat was at 100%. That's why, especially in pediatrics, who are more prone to oxygen toxicity than adults, you maintain saturation between 94 and 99. Okay? You can measure this easily with a little O2 satometer. PaO2 has to be measured with an Abg. Now there are other things that affect this curve. Temperature does, pH does, as you can see in the little thing here. This is really not why we're here today. Matter of fact, this lecture is not about oxygen at all, because oxygen has no bearing on pH. I'm just getting this oxygen out of the way. It's kind of a, you got to have oxygen to live, so I might as well talk about it for a few minutes. If you're not getting oxygenation, then here are some issues here you should be considering. Do you have the intubation? Do you have the ET tube down the esophagus? That would be a good thing to check. Is it blocked? Is the ventilator not working? Is cardiac output affected? Cardiac output. Let's talk about that for a second. What determines gas exchange? What determines gas exchange in the lungs? Is it the bagging? Is it the ventilator setting? No, it's cardiac output. That determines gas exchange. If you have no blood flow through the lungs, you will have no gas exchange. If you're measuring CO2 as a measure of gas exchange, if there is no blood flow, there will be no CO2. If you intubate the esophagus, there's no CO2, right? If you have a big saddle embolus of the pulmonary trunk, where there's no blood flow going through the pulmonary artery, even though your ET tube is slammed dead in the middle of the trachea, you're going to have no CO2. Understand that? Okay. Well, here's some ways to measure oxygenation and CO2. Here's a pulse ox here. You put it on the finger, measures it through the nail. It doesn't work if you have gloss or fake nails or painted fingernails. You got to get them unpainted. That's why acetone is always in the ER. In little babies, you can measure oxygen saturation through the skin or through the earlobe in a kid, in an infant. On this side over here, what we're measuring is CO2 output. If we have an endotracheal tube sticking out of a person, we're going to put this little thing right here called a CO2 detector on it, and then we're going to put the bag on that detector. Every time, after about 5 compressions of the bag, and the patient breathes out, you know, as you're doing chest compression, it's exhaling CO2. The presence of CO2 after about 5 ventilations will change that filter paper it'll change its colors. So the mnemonic about what colors it's supposed to be if there's CO2 there is this right here. Purple problem, tan think, yellow yes. So when you pull it out of the pack, it's purple. After about 5 ventilations, if you're in the trachea, the CO2 will change it yellow. Purple problem, yellow yes. If it's in the right main bronchus, if you put the tube down too far and it's in the right main bronchus, because that's where it would go, right? Because it's shorter, narrow, and more, it's shorter, wider, and more in line with the trachea. That's where it always will go. You'll get a color change, but it won't be yellow. It'll be the intermediate color of tan. That's why you think, oh, what am I doing wrong? Ah, I got it in the right main. Pull it up. Rebag, make sure it turns yellow. So that's the dumbass little mnemonic to remember what, because you're going to do 5 ventilations, you're going to look down at that filter paper and you're going to say, crap, what color is it supposed to be now? That's the thing. Purple problem, yellow yes. That's qualitative. We want quantitative. Quantitative measure of CO2 is called capnography, waveform capnography. When you breathe out into an ET tube, there's a pressure sensor on the end of it. Instead of a CO2 detector, there's a pressure sensor that measures millimeters of mercury of expired CO2. Normally, it's up around 35 to 40 millimeters of mercury. So this is breathing out, and that's breathing in. The drop is when you breathe in, right? That point right there before the drop is called the end-tidal CO2, the PET CO2. End-tidal CO2. You can see these things when you look on them. You're in the ICU, you can see these things on a monitor. So during cardiac arrest, this goes way down because you're not moving air. You're not diffusing like you normally do. Your cardiac output in chest compression is only around 30% of normal. So instead of 35 to 40 PCO2, you're only down around 10 millimeters of mercury. If you are indeed in the trachea with your ET tube, if the PET CO2 drops below 10, how do you get it above 10? How do you get it above 10? How would you get it above 10? It's an easy answer. What?
What was the situation? You had it.
So you're doing CPR on somebody. They're arrested, and you've got an ET tube down, and you've got a waveform capnography pressure sensor, and it's you're bagging. I mean, they're on a ventilator, and or you're bagging. It doesn't matter. And normally, if you breathe out right now, your PCO2 is 35 to 40 millimeters of mercury. But in cardiac arrest, like I say, it goes down to 10. It goes down to 10 because your cardiac output in chest compressions is only about 30% of what it is now. Your ejection fraction is like 60 milliliters of blood. In chest compressions, it goes down to like 20. So you're not putting as much blood out, right? So if your PCO2, if your capnography goes down to say 5, how would you get it up? Improve chest compressions. It's not a ventilator setting. It's a cardiac output setting. Do you understand now? Okay, everybody follows that. Okay. All right, so here goes, so forget oxygen. We're not dealing with oxygen. We're going to deal with pH of blood. We have somebody in cardiac arrest. Obviously, we have to be concerned about oxygenation. Make sure we've got the ET tube in the right place. Make sure they're satting okay. But we got to worry about the pH because they're not breathing. It's not going to be good. Okay, so there are a couple of formulas that you need to know here. One of them here is we've got carbonic acid is formed by CO2 and water. CO2 from your normal metabolism forms with water to form carbonic acid. You take the equation further to the left,
that carbonic acid can break up into hydrogen ion and bicarb. So that's the formula there. You can get rid of acid a couple of ways. You can get rid of hydrogen ion, or you can get rid of CO2. If you get rid of CO2, you're not going to form carbonic acid. Right? That's simple. If you get rid of CO2, if you retain CO2, you're going to form more carbonic acid, you're going to form more hydrogen ion. So one way to affect pH is just your respiratory rate. It's that simple. Okay. Now, normal metabolism, though, forms a couple of different types of acids through just normal metabolism. Respiratory acid is what we're describing here as carbonic acid. It's a weak acid. It's a weak acid. Strong acids, though, are formed by normal metabolism of other substances. We list them here, larger molecular things from fats, carbohydrates. Anaerobic metabolism forms lactic acid. Lactic acid, right? Lactic acid. You go run a marathon, you get lactic acid buildup because of the metabolism. You switch to an anaerobic metabolism, right? So here's lactic acid over here is a strong acid, as well as other acids that are formed in the body. Strong acids will react with a salt called sodium bicarb. Sodium bicarb to form carbonic acid and the salt of that acid. Once you get to carbonic acid, then you can take it a step further, and here you have CO2 in water. And then you can get rid of the salt, either by peeing, pooping, or through the liver. Or all three. Now there is an error on this thing here. You see that arrow right there shows it going both ways? It doesn't. It only goes this way. It only goes to the right. When you reach this one right here. This one right here can go back and forth, but that one only goes to the right. So that little arrow right there, cross it off. You see which one I'm talking about? That one right there, cross it off. Any questions about this? Buffer systems. How do you, if you're forming acids all the time, how do you keep your pH within a narrow range? 7.35 to 7.45. That's your normal range of pH, 7.35 to 7.45. How do you keep your pH within that range? You do it by buffer systems. And you have a whole bunch of buffering systems in your body. The most important buffer system, but what is a buffer system? A buffer system is a weak acid, is a solution of a weak acid and the salt of that weak acid. So if I go back to here, there's the weak acid and there's the salt of the weak acid. So sodium bicarb and carbonic acid are the two elements of the most important buffering system of your body. There are other buffering systems, and one of them is kind of interesting here, is hemoglobin is itself a buffer. Why is hemoglobin an issue here? Think about it a second. What is an RBC? It's a bag of hemoglobin. That's it. It's got a few structural proteins in it, but essentially it's a bag of hemoglobin. If it dumps out all of its O2 in the periphery and takes in nothing but CO2, what have we already said about CO2? it's going to form with water carbonic acid. This hemoglobin is a buffer to prevent the pH shift within an RBC. That's kind of cool. Makes sense. All right, you're ready? Okay. Now, when you look at the weak acid to the salt of that, the ratio as it exists in the body, that determines your pH. Everybody knows that the pH is on a logarithmic scale, right? So if you look at the ratio of one to the other, I mean, what is pH? The pH is a measure of hydrogen ion, right? If we look at the ratio of sodium bicarb to carbonic acid, it's 20:1. You can't, if there's a change in this ratio, the change is going to occur in the acid. If you hold your breath, you're going to retain CO2. That's going to combine with water to form carbonic acid. You're going to change the denominator. Understand that you can't change the numerator. You can't make more sodium bicarb because there's a rule here. Because an acid cannot react with its own salt. If you go back to this, you can't go that way. An acid can't react with its own salt. That's why I said take off that arrow. You can only change the denominator. If you change the denominator, because this is logarithmic, it makes a huge difference in the concentration of hydrogen ion. In fact, the change of 0.3 in pH will either double or half the amount of hydrogen ion. That ain't good. If your pH goes from 7.4 to 7.1, so you're making the solution more acidic, then you double the amount of hydrogen ion in your body. If you go from 7.3 to 7.6, you're making it more basic, you have to. So small shifts in pH produce monstrous changes in hydrogen ion. That's why your enzymatic system, your enzymes in your body, this biochemistry doesn't work in an acidic solution. Everybody following? All right. These are the normal Abg values. When you get an Abg on somebody, you get these four things. At least these four things. You'll get the pH, as I said, 7.35, 7.45. You'll get the partial pressure of oxygen, 80 to 90 mil. We don't even care. When we get an Abg, I don't even look at PaO2. I'm looking at PaO2 only through the oxygen saturation. That's how I'm gauging PaO2. I am looking, though, at PaCO2 because CO2 determines the pH. And it's only the CO2. They also give you bicarb here that we'll use here in just a little bit. Now, regarding the pH, we're going to use 7.4 as our reference point. And for PaCO2, we're going to use 40 as the normal amount of CO2. Now, there are three golden rules that you have to know to calculate, to interpret ABGs. The first golden rule here is that for every change in PaCO2 of 10 millimeters of mercury, that's going to translate into an up or down, depending on whether or not PaCO2 went up or down, into a pH change of 0.08 units. The second golden rule we'll get to in a minute involves bicarb, for every change of 10 milliequivalents per liter of bicarb, it will change the pH up or down of 0.15 units, pH units. All right, so how do we work this? So, using golden rule number 1, if we have a patient that comes in, we get an Abg on him, his pH CO2 is 50. 40 is our reference point, right? It's gone up 10 millimeters of mercury. If the pH CO2 goes up, that means the person is retaining acid. pH will go down. You follow me? So using golden rule number 1, if the pH CO2 has gone up 10 millimeters of mercury, it's simple. For every 10 millimeter change in CO2, the pH will adjust by 0.08. So because it's gone down, because you have an increase in CO2, you subtract it. 7.4 minus 0.08 is the calculated pH of that person should be 7.32. Okay? It should be 7.32. If it's 7.32, if you get what you calculate, then the person is in respiratory, because it's CO2, acidosis. And it's acidosis because it's lower than 7.35 to 7.45. If the calculated pH approximates what you actually get or have on the Abg, then it's pure respiratory. It's pure respiratory. If not, then there must be something driving that pH in a different direction, either further acidic or basic. There's one thing I forgot to cover earlier on, is right here. There are 4 things we're going to talk about today. Respiratory acidosis, respiratory alkalosis, metabolic acidosis, and metabolic alkalosis. Those are the 4 diagnoses you're going to pin to something. You're going to pin to an Abg. So if the calculation approximates what really you find on an Abg, it's pure respiratory. Okay, now in this example though, the PaCO2 is 50, same place, same place. So 50 minus 40 is 0.08, right, 0.08. You put it in the formula. The calculated pH should be 7.32. It's the same. But well, wait a minute, this guy's pH is 7.26. Now we go to golden rule 2. We subtract the calculated from the actual, and we get a difference of 0.06. Remember I said in terms of bicarb, well, wait a minute. Since it's 7.32, this person is in respiratory acidosis, but something is making them more acidic. So if we take the calculated minus the actual, there's a difference of 0.06. Put it in this ratio here. For every 10 milliequivalents of bicarb, it changes the pH of 0.15. Solve for X here. X is 4 milliequivalents per liter of bicarb. This person is in, the diagnosis here is respiratory acidosis and metabolic acidosis, because there's enough lactic acid that keeps driving the problem down. It makes sense, right? You treat this problem, and you would treat this problem, you can do it 2 ways. You can address the carbonic acid by blowing off more CO2. You increase the ventilatory rate. And you can also affect the strong acids, the lactic acids, by throwing a little sodium bicarb in there. So by throwing a little sodium bicarb in there, you're going to drive the equation this way, the carbonic acid and then the CO2. Got it?
Do you have to increase the ventilations even more once you start pushing the equation to do the two problems?
You're going to be monitoring them along the way, and slow it down, speed it up, depending on what the pH says. Okay. So that's pretty easy, right? Okay, but what does this mean here? What does that 4 milliequivalents per liter mean? That means per liter of all your extracellular fluid. That's per liter of your body, your whole body. How many liters do you have in your whole body? Well, that's when you get to this calculation. This is essentially golden rule 3 here. Now, you can work your way through all this business right here, and it's essentially what I told you the other day about extracellular fluid. The bottom line is the base deficit, which is what we were dealing with. You were deficit sodium bicarb at a rate of 4 milliequivalents per liter. How many liters are in your body? If you look at the extracellular fluid, well, it's essentially, the extracellular fluid is essentially 1/4 of your total body weight in kilograms. Now, you can go through all of this stuff here about the percentage of your body weight being 1/3 and all this kind of bullshit stuff, but bottom line is you take your weight in kilograms, divide it by 4, and that's your extracellular fluid. So your total body deficit is in golden rule 3. If we take the base deficit of 4, in that example I gave you earlier, and multiply it times your weight in kilograms, not pounds, kilograms, divided by 4, the person is in a total body deficit of 70 milliequivalents per liter of sodium bicarb. So in order to correct that pH, even if you didn't do anything to the ventilator setting, if you gave them 70 units of milliequivalents of bicarb, sodium bicarb, you'd fix their pH. An amp of bicarb that you inject in somebody, sodium bicarb, is 50 milliequivalents. So if I gave this patient 1 amp of bicarb, I'm going to get them almost fixed. I'm going to get the pH from 7.26 on up to normal range. Make sense? Eddie? Scratching your armpit? Okay.
Would that treatment for respiratory acidosis and the metabolic acidosis?
They're still in respiratory acidosis. The pathology is still there. Why are they in respiratory and metabolic acidosis? It may be because they're in arrest or diabetic ketoacidosis. For whatever reason, it could be hyperaldosteronism. It could be anything. The issue here, it could be antifreeze poisoning. It could, a lot of things. Antifreeze poisoning causes metabolic acidosis. So it could be a lot of things. This is only to address the pH. Now you've got to figure out the disease process. You're going to give them insulin and fluids. You're going to give them, what's the antidote for antifreeze? What's the antidote for antifreeze? Alcohol. You give methanol. Antifreeze is degraded by alcohol dehydrogenase. Flood the dehydrogenase with ethanol, and you wind up eliminating it's the metabolized antifreeze that kills you. It forms phenol or formaldehyde. So flood the enzyme with ethanol, and you pee out the unchanged antifreeze. That's the treatment for it. Okay? Right.
But when you're saying increased respirations, is that like on a ventilator specifically?
Yeah, on a ventilator, or you can bag them. If you're bagging them, you can slow down your. Okay, here's an example. You're all going to run into this. You've got a 16-year-old shows up into the rural emergency room. I don't mean to be sexist, but everyone I've ever seen is a female. They are, she just caught Carl with Rebecca underneath the bleachers over at the high school, and she's just, and you know, she's been drinking with Lily, and I can't deal with this type of stuff anymore. I'm just, what is she doing? She's blowing off CO2. She's blowing off CO2. What happens to her? She gets lightheaded. Mom, I can't feel my fingers. I can't feel my lips. What am I going to do with? I think you gave me herpes. I mean, it's just, she comes in with 10 of her friends. Right, Tim? What is the treatment for that?
Read into a bag.
Yeah. For a bag. Breathe into a bag. So she's blowing off her CO2. She's becoming alkalotic. Get her to breathe CO2. Her pH comes back down to circumoral paresthesias, her fingers tingling, and she's good to go. Other than whipping Carl's ass. Or having her brother shoot him. So it's all a matter of, and it's acutely. So in a cardiac arrest, you can do it by increasing or decreasing the compressions of the bag. You should compress the bag every 6 to 8 seconds. But the first time you start bagging somebody, your sphincter is going to be up around your highway bone. And you don't breathe like that because you're blowing off all the CO2. You're going to make them alkalotic. So slow down every 6 to 8 seconds. Squeeze it over 1 second. Does that help? These are true stories. I'm not kidding. True stories. Everybody follow me here? Now you don't need to correct pH all at once. You can do it, if it's not too far out of whack, you can do it slowly. You know, 70 milliequivalents, I'll just go ahead and give them the whole amp. If you calculated this and they were like deficient 240 milliequivalents, I wouldn't give them 240 milliequivalents of sodium bicarbonate. I'd give them an amp, wait 30 minutes, recheck an ABG, recalculate, maybe give them another amp, so you're correcting it over hours. Now, if your ABG is out of whack, but your pH is within 7.35 to 7.45, it's called compensated. Remember I told you that, I gave you the example of the emphysemic guy. His PaO2 was around 60. Yet his PaCO2, because of air trapping, he can't expel with air, his PaCO2 was up around 60 as well. But in this chronic condition, if he's not having exacerbation, his pH is 7.4. How is that possible? How is it possible that his PaCO2 could be so high if you calculate it? Let's calculate it. Okay, so his PaCO2 is 60. 60 minus 40 is 20. For every 10 millimeters of mercury change in CO2, what does it change the pH? 0.08, right? So there's 2 times that. We should have a change of 0.16. Because CO2 is up, pH should be down. His calculated pH should be 7.4 minus 0.16, or 7.24, right? That's his calculated pH. But I just told you, his pH is 7.4. He's compensated for that respiratory acid. He's in respiratory acidosis, but it's compensated. It's compensated because his kidneys have retained bicarb. If you looked at his bicarb, it would be up as well. You follow me on that? Here are some examples here, hyperaldosteronism, just nice examples.
So would you just essentially use up the kidney's bicarb stores and then the pH would drop to the calculated if nothing happened?
No, he's probably gonna wind up, while he's in your emergency room, is he can't breathe. His PaCO2 is gonna continue to go up. And your kidneys can't compensate that fast. So the pH will go down. Remember that the kidneys take about 24 hours to compensate, right? Because you're talking about urine output. You can change PaCO2 into pH with the lungs very quickly, like we saw with Carly. Where's Carly? There you go. Carly in our histrionic self on the Friday night, under the bleachers with Loomis. Okay. So here's essentially the primary disturbance in these different conditions, and this is how your body compensates for them over here. Kind of summarized. If you don't understand a damn word I've said today, then this is your out. It won't help you calculate base deficit for the amount of sodium bicarb you need, but it'll at least get you the answer. If the pH is if the pH is decreased, it's acidosis. If pH goes in the opposite direction, excuse me, if the PaCO2 goes in the opposite direction, then it's respiratory. If it goes in the same direction, it's metabolic. Okay? But you're not going to have to resort to this. I can promise you there will be at least 3, if not 4, ABG interpretations on your national board exam. I can promise you that. So knowing this quick calculation will get you the answer. All right, so let's practice. Let's practice, okay? So give me a second, let me pull this thumb drive thing right here.
That is smart.
Yeah, that makes sense.
No, I say this, but I don't.
Can't tell you what actually
There's a way to do it, and there's an answer, and it's not the way to do it.
Okay, you need to take a quick break or?
Let's do it.
Let's do it. All right, here we go. All right, so you don't have to work by yourself. You can work in partner up. First. I'll need to get out a piece of paper and get your calculator out.
At least we don't have to do negative logs.
What's that?
40 is our reference? Or
Yeah, use 40 as the reference for CO2, 7.4 is the reference for pH. I'm gonna give you the answer here in the next slide.
Oh.
That's we have changed at least 10 changes of 20. I'm just basing it off that. It's in intervals of 10. And that should be what the pH change is, but since it's not, then you'd have to subtract 10. I know.
Yeah.
That's your reference. That's the reference range for pH always. So 7.40 and 7.4 are our references.
Those are the golden ones.
Oh, yeah.
Oh shoot, I didn't see okay, so I did it. So you start at scratch is where you start from base. I did it based off of 10 and it's 12. So this body is 12. Still over 0.15. That's what
Oh wait, I messed up.
Still like based off those, so I 2%. I got always a very bottom side.
Like if you're saying it's fish.
So the point of
What did you do?
And then to calculate how much sodium bicarb to give.
I mean,
is the base deficit times the weight divided by 4. The base deficit times the weight divided by 4. To determine how much sodium bicarb you get. Correct.
Okay, so let me cover a couple of things here before we reveal the answer. So I can look at this and I can tell you that with CO2 elevated, and he's acidotic, he's going to be in respiratory acidosis. But CO2 is only elevated 12 millimeters of mercury. Remember, 10 will only get to 0.08. So something's driving this down further. So this is, I can tell you, just looking at those two numbers, this is respiratory and metabolic acidosis, and it's outside of 7.35 to 7.45, so it's not compensated. That's the answer. Okay. Without even calculating, I can either look at CO2. If 10 will get you a change of 0.08, this is only a 12 difference. All right. So let's actually do, well, let me add a couple of other things. When you calculate these things, and there's actually a base excess, if you're in alkalosis, you can get a base excess. Remember, if you have a base excess, then you don't give somebody acid, right? We're not going to inject you with acid. Okay, I just want to make that point. How can you wind up with a base excess? Think about somebody with profuse vomiting. What are you throwing up? Hydrochloric acid. So you're going to become alkalotic. And you'll wind up with a base excess because of that. At some point, I'm going to talk to you about chloride sensitive and chloride resistant metabolic alkalosis, so we'll go over that in more detail later on. Okay. So here's the answer. So we've got up at the top there, 52 minus 40 is 12. We put it in the ratio, 10 over 0.08, 12 over what is 0.096, which is essentially 0.1. Everybody got that? That's rule number one. So since PaCO2 went up, pH should go down 7.4 minus 0.01. The calculated pH should be 7.3. That's respiratory acidosis. But his actual pH is 7.17, 7.3 minus 7.17. The difference is 0.13. Put it in golden rule 2. Calculate X. The base deficit is 8.66, which is roughly 9. The guy weighs 70 kilograms. Take the base deficit times 70 divided by 4. His sodium bicarb is 157 milliequivalents per total body to bring him up to normal pH. So he is in respiratory acidosis with metabolic acidosis, not compensated. Everybody get the right answer?
Okay, I didn't round on some of
You
them.
do not have this on D2L. This is not on D2L. Does it make somewhat sense now? Sarah, you just look like you're having gas.
Yeah, that last slide was like how else Bill can write this. That was where I'm at.
Which one?
The last slide was like how else Bill
Yes, because you're going to have to do this on the test. You can take a picture. Well, I'll send it to you. I'll send it to you.
And then you use this one.
I just don't want it to get into next year's class. That's why I don't share it next year's class. okay?
Now, they can round it.
That's the same thing last year's class had about you. Well, you don't have it. All right. Any other questions about this? Sarah, do you have a specific question along here? Here's golden rule 1.
Right.
There's golden rule 2. There's golden rule 3. Right
Start
there.
getting lost around the base, that's it, like I got the first.
Yeah, so just take what you've calculated, 7.3, that's what, but that's not actual.
Right.
Let's
That's his actual.
calculate it.
So something's driving down to make this difference here, and that's the metabolic component. All right, let's try another one.
You have a piece of paper. Form notes. You're next. Let's see if I can get this done. 70 kilogram PaCO2 31 alcohols.
That last example would be like an emphysemic, by the way.
It's just 7.29.
This one right here, you're blowing off CO2. So this is our histrionic Carly. Always make the numbers positive. Don't say 31 minus 40 equals minus 9. Always make them positive. 40 minus 31. It's a ratio.
Nine over 10.
Well, no, the pH is still down.
So you need to find out exactly.
Might be metabolic.
0.072.
She'll be pulling. 0.7. 0.7. Oh, yeah.
Do you still put in, do you put in fat or just in oils? To get 0.072? That's what I got.
They're constants.
Minus 7.472. Golly. Thank you.
Yeah, I'm
Did
stuck.
you get negative 0.182? Alkalosis. But we still use positive numbers.
Yeah, I have 7.
I think we said all the respiratory osmosis and it's gonna be 0.18, and then you do the exact same process.
And metabolic is just much more.
Because it's gonna be metabolic.
No, the acronym.
Metabolic acidosis.
Right. So you literally do the same process.
Or there's a complicated
Because it,
So it would be 7.
Do you know what the last step is?
7.0.
After I get to here.
7.29
Well,
minus.
I mean, fairly low. Sorry, fairly acidic. Yeah, sorry, I go the same way. It's kind of
I think that's one caught up to it.
I mean, I'm pretty sure it should always make it positive.
always make it positive, like you're just making the numbers.
You're just trying to find the change.
Yeah, but it's gonna be negative, and then if you subtract 7.4 minus this, it's gonna be a positive.
You don't,
Here.
I don't know.
0 point, this one?
Explain it better. I don't know. I really.
Yeah, because it's low.
Okay, let's go over this one. 40 minus 31 is 9. 9 over x equals 10 over 0.08, which gives us 0.07. The PaCO2 went down, so the pH should go up. So at 7.4 plus 0.07, the calculated pH should be 7.47. He's in respiratory alkalosis, but he's not alkalotic, obviously. So we take our calculated pH, 7.47, subtract his actual pH, 7.29, 0.18, put that in our ratio here, solve for x. The base deficit, we know we're in a deficit here, is 12. He weighs 70 kilograms. 12 times 70 divided by 4. His base deficit is 210 milliequivalents. Not milliequivalents per liter, milliequivalents. That would get his pH back up to normal. So this guy is in respiratory alkalosis with metabolic acidosis. Again, it's not compensated. Where did you get it?
You asked me on, why did you add the 0.07 instead of subtract like in the first?
Because the pH went down. I mean, excuse me, PaCO2 went down. PaCO2 is the acid. If you lose acid, you're going to be more alkalotic. Right? So when I first look at this, I see a PaCO2 of less than 40. I'm thinking this guy's alkalotic. He's got to be alkalotic. But whoa, he's not. So I can already say he's in respiratory alkalosis, but he's in big time metabolic acidosis. And this is somebody who's breathing off their CO2. Did anybody get that one right? We got a couple. All right, so we're going to, all right, let's do one more.
But I got it because pH is still going down.
How would you know if it's, okay, so would you know that it's compensated if it's still, if the pH is normal?
If the pH is 7.35 to 7.45.
Yeah.
I mean, I understand how to do the math. I have to
The
understand
actual pH.
what's
Yeah,
up
yeah.
there.
Yeah.
Hey, Paul made a very good point. Paul asked a very good question, very good point. If the actual pH is 7.35 to 7.45, it's compensated. If it's not within that range, it's non-compensated. Not any calculated pH, it's the actual pH. Okay, here's the next one.
Really, the biscuit as long as it always if those will determine if they're respiratory or whatever another. Right? Oh. I'm gonna have to like think about it. Okay. Okay.
tuberculosis. When it's low, respiratory and metabolic alkalosis. Calculate treatment.
It's for every, and it goes down.
0.08.
I guess it's down to, yeah.
Do you still subtract?
Just 0.8.
Because you just subtract and then.
Oh, you're good.
Base deficit. 70 over 4. Mercury. Goes to delta pH.
Over 10.
0.08.
0.5 over 10, yeah.
0.4 plus 0.8. 7.48.
So that's the base deficit. So you take the base deficit times 70 over 4.
Yeah, so the difference between the two is
190.1.
Do you know how to
So I did times subtract
instead of added?
The sodium bicarbonate.
Yeah. I use 0.08.
So he's
So
supposed
does
to
add
respiratory
7.1.
Yes.
metabolic
And that's why I was like,
So then that's a change. And then
okay, where did you get that?
again, alkalosis.
Oh, okay.
PH is going more.
Oh, no. So you calculate the 7.48 is calculated, is actual
pH is high.
7.48. Delta
Right,
is
yeah,
0.01.
higher than
Yes,
yeah.
yeah. So it's alkalosis.
Here's the last part of that though. The pH increases alkalosis, which again, and then is
I don't
CO2 is down.
the base deficit.
Too. So
CO2 is down. So alkalosis. So he's respiratory alkalosis and metabolic alkalosis.
0.01
So
divided
the change in base, if you change 0.15, so a change of 10
of mercury.
of base
Okay,
is a change of 0.15 So then this is what number we So then I multiplied this, so that's 0.1 divided by 0.15. Get 0.7.
Oh, okay, so you solve to get 0.7.
Yeah.
X equals 0.7, which is the base deficit.
Right.
And then you use that to calculate.
multiply that with this.
Okay, so 0.7 multiplied by 7. It does. No, that's it makes sense. I'm
Actually, maybe this is more
so 12.1.
I had them both held. It's just on the calculator. So what is, and I just like to what's the tip for the base deficit?
The big three,
That's what I got to.
so 40 minus 30 is 10,
Yep.
which is gonna give you 0.08. Because CO2 went down, pH should go up. So the calculation
should be 7.48, which is the exact, almost to the 100, what it is. Here, respiratory alkalosis.
Yeah.
Give him a bag.
Easiest one we've done.
Yeah, that one.
Oh, you're not done yet. The what?
What do you do if he's like super high and like he's in metabolic output?
Well, he's almost, it's not
So what
really,
about like 7.6?
it's not really bad.
Oh, really?
I mean, yeah, it's not. What are you asking for?
What else is he like 7.6?
So why did it?
7.6, let's still give him a bag.
Still give him back.
You're not gonna give him, let me just say that, Ian asked, what if it's, wonder if his, pH was 7.6. Remember I said that metabolic alkalosis can be either chloride sensitive or chloride resistant. An example of chloride resistant would be hyperaldosteronism. You fix the problem.
Okay.
If it's chloride sensitive, that means giving them chloride will fix the acid-base disturbances. And I gave you the example of somebody throwing up. Just give them saline, which is what they need because they've been throwing up. You give them chloride through saline that restores the hydrogen. And there you go.
How do you know?
Huh?
How do you know which is the case?
Well, I can tell you, it's pretty easy to tell the difference between vomiting and Conn's syndrome. So, I'm just saying, if I got vomit on the floor, it's probably but not, you're not a valid point, you know, it could be something bizarre like Barter syndrome. Who the hell has ever heard of Barter syndrome? That's an example of chloride resistant metabolic alkalosis. So we'll get into that later, I think. All right, here's next.
Yeah. I don't remember. But I'm sure we did. We're after we watched it. When next week stay with?
Yeah, there's a bunch of stuff.
Olivia? Hey, Snooper pickle, please. Thank you. What happened to this one? What happened to this one?
Some use acidic.
I mean, like from 7.3. Like this, right?
20.
Oh, I was like the first.
So right now I'm just finding the cheat. That's what
Let's see. The difference is 20. About 1.6. Subtract. So 7.5.
Yeah. So then. Question. Is that close enough?
I did too.
You know, like the last one we just did?
Yeah, 0.02. I don't know. Too close? Yeah. So delta is 0.02. What is that value called?
It's just, it's times 2, so you just, it's 0.16. So 20.
Delta pH.
Like, .8.
The value is 0.16.
I thought that they stuck it.
Right. 0.08, so you just put the 0.08, 2, finish up 2, 20.
And then being
I mean, you can calculate that
I
later,
might be doing redox then.
but it's
You
just
don't
gonna
have
be
to
0.16.
until we're gonna do this.
Okay, so where's that?
Because if you have pennies, yeah, it's like just double, it's $1. So if it's double,
You do this
What do you
minus.
0.15.
or minus
Oh yeah, so
1.16 to 7 point,
minus 0.1.
equals 7.24.
Okay, next step.
So that's your reference. Then I'm
Is
stuck.
there, we're
01 over
subtracting
X.
because
02 over
he's
X.
an acid, right?
Change a point over.
We're subtracting because he's an
402 times 10 is 0.15. 2 divided by 1.5.
60 minus 40 is 20. Put in the ratio 0.16, because PaCO2 went up, pH should go down.
4.8.
7.4 minus 0.16, the calculated should be 7.24 for respiratory acidosis.
That's it.
Well, that's what it is. It is pure respiratory acidosis. He's not compensated. So one of the ways to fix this would be to blow off some of this CO2 by turning the ventilator setting up. You look confused. Huh?
Wait.
I guess, did you like give us a rule? I'm stuck on like the pure alkalosis acidosis, like when do we know when to stop and when to calculate the base steps?
Yeah, so
Well,
Did you get 4.8?
Yeah, so I gotta change and from
here,
calculated.
it's, the calculated is just about the same as the actual.
At what range, when it's different, would you even consider doing the math for the metabolic acidosis?
Well, there's,
Like-
right now, there's no metabolic component to this. So right now, there's no metabolic component. It's all
Respiratory.
ventilation. So to fix it, change the ventilation. Now, if this patient came in here, like if they had a traumatic brain injury and they weren't breathing fast enough, they were only breathing 8 times a minute, they're retaining CO2,
Solved, right?
then the quickest thing to do, instead of giving them sodium bicarb, is intubate them, get them on a ventilator, crank up the ventilator setting, get their breathing up from 8 a minute to 16 a minute, and they'll blow off this CO2 and they'll normalize themselves.
What I'm asking though is when the difference between actual and calculated, if it's like 0.1, would we go ahead and try and figure out, because this is 0.02, and the one before it was 0.01, and you said it's close enough, it's pure respiratory. And so how much of a difference until you would consider doing the math for metabolic? Does that make sense?
If it was probably more than 0.05 or
05?
0.1,
Yeah. Because on the first example, it was 1.3.
Yeah,
So there's a
1.3,
lot,
yeah.
yeah. I just didn't know what the cutoff before you wanted us to do that.
yeah, I'd say, you know, maybe 0.1, just go with 0.1. Now, if you're calculating 7.3 here, then I'd say that's close enough. You're gonna fix it by just blowing off CO2. Now, you could give this person bicarb, sodium bicarb, but that's not really the issue here. It's not a metabolic issue, it's a respiratory issue.
1.3.
Okay?
You had it right.
Let's see how many more I got. I got just a couple more to go, so. I think they're only
Plug that
2
in
more.
there. Here we go.
Just about.
Oh, 7.14. Right. Those are the same. So 7.4. said between 7.35 and 7.45. That's normal. Yes. Increase. Yeah. Increase. Compensated respiratory.
What it is, I don't know.
So,
I don't know, I'm sorry, I can't give you like explanation, I just really don't know why.
change this morning.
Sorry, can you say that? Is that a shame? So what do you mean?
Respiratory acidosis.
So would you have to give them that? I guess you have an idea. I didn't
Acidosis.
You wouldn't even
It's not a CO2. I don't know. Wait, but if it's compensated,
like, do I have to have this?
so there's too much CO2. Increased CO2 means increased acid. Increased acid means acidosis.
Oh.
But this one's compensating.
Oh, I'll do this.
You just define it as
I'm not adding anything.
3, 5, 6, 4, 5.
Unless you're in alkaline state.
So none of these kids need to be added.
I get
We
what
have to read what's the
You see what I'm saying?
Yeah.
Like, I don't understand.
Oh, let me see.
So is it the 0.115 over 10?
Right. So the what?
I think it's an
Right. So it's, yeah, it's
Okay, that's what I
compensated.
did. I got 12, and then for sodium bicarbonate, 10.
Yeah.
I got 2, I don't think that's right.
Okay, so what,
Wow.
do you still need to calculate this?
Like, to understand this math, I have to understand each step on why you do something. I don't memorizing it doesn't help me on math.
So it's pretty much the same one from before, so 7.24,
Not
right?
helpful.
I'm just gonna like,
It's the same as before.
like I understand the steps, but I don't understand when to add and when to subtract.
No, I got what you were saying.
Oh,
on
okay,
the
okay.
pH thing.
Yeah, like that's where I get stuck every time.
Minus
So this is the base steps that
0.16
That's what I got.
7
And so for every 10 changes,
when you buy the milk, that they share it, not base.
and so we're taking this ratio. What'd you get? So we're taking that ratio and finding out what it actually changes.
Did you round it?
Did you round from
Oh, you did?
I did it.
Did you get 2 tens?
I did, yeah, I got 2 cents, I didn't
I
round.
didn't.
for basic deficit?
I was just making sure I
Sorry,
did
no,
it
I'm
right.
just starting from the beginning. Okay. So,
I mean, I don't know, I probably didn't do it right,
0.16
so.
Well, if
calculate
you're about to say it, I got the same.
But I'll just wait.
It's kind of unlikely.
I just don't understand. I just like,
is
What
subtract.
What do you not understand?
like
Like,
for
so this is
the,
a,
like I understand to subtract or add this, but then after you like subtract from
It's
the,
because of the CO2.
I don't understand the pH adding and subtracting. I don't get that.
I said
You're just looking for the change.
yeah, I know it
the
says that's right
CO2
here,
didn't go down.
but
It's like on this one we added because.
Okay, here we go.
This one you add up. See, on this one you add CO2 went down.
Still the same 7.24, right?
They look at the CO2, they don't look at the
Calculate.
I mean, I just.
So then, respiratory acidosis, right? But it's compensated because it's 7.35 to 7.45. If you want to do the calculation here, you can get to base excess, but he's already taken care of the issue. This is the emphysemic that chronically has retained base to get him back to compensation. Okay?
I have a question.
Yes, ma'am.
You gave us this
Yeah, we don't have to.
chart. And in this chart, it says that it's compensated metabolic alkalosis. Because the pH increased and so did the CO2.
You're looking at the metabolic acids.
Yes, he has a base excess.
No, I said I don't understand why.
He has a base excess. That stupid little chart, that is, it's right.
I don't think it's stupid.
Okay, let's do the last one.
My head is hurting.
I don't like it. I don't like it. I like your chart.
And you need to get bicarb to get normal by turning it on. And so you know that this much excess, that's offsetting the respiratory acidosis. Yeah, I mean, they're compensating. So instead of almost because you compensate slowly. I don't crash or get off.
So then we just pull out 47. Yes, right? Yes. So, okay. No. So CO2 below 40, that's in the end. Just remember that.
I don't understand the pH though. That's my problem.
Don't listen to that. Okay, so.
So
there's a difference. We add 28. Target.
Okay.
Let me look at that.
Then you go to 7.4.
Oh wait, no, wait.
7.4, you have to do something like this number now.
Hold on. So then we.
Okay. Okay, so compensate. No, not compensated. Outside of finish. Alkalosis.
Down by 30.
40 minus 30, it's 0.0. Alkalosis. Non-compensated.
You get it? Is that what you did?
40 minus 30 is 10. 10 is 0.08.
Oh.
CO2 went down, calculated to be 7.48, which is exactly what it is, to the letter. So this is respiratory alkalosis. It's not compensated, but it's close. It's close. Now, clearly on the exam, I'm not going to give you one that's 100th of a point off, so it's going to be pretty far off. Calculate the base excess here, it's 0. There is no base excess. So, everybody understand everything going on in the world? Okay, so on your D2L, there's a sample ABGs, there are about 20 of them. I would suggest you guys go through them, come together as a class, and just somebody read all, this is what I got, and if there's a discrepancy, then let me know. Okay?
I'm still
Are the answers you know this?
No. That's so funny.
Which is so funny. I gotta
Hey, what's the name of that place where you write poetry? You good?
Yeah, that's a
what?
Having the like challenging or like having to think about it.
All of my other program was biostatistics.
I took biostats, but it was so long ago.
It was actually kind of fun when it works out. Oh, like, yes, like that moment where you finally think and get it, and it's like, thank God, because otherwise big. For 2 reasons, that was good.
That moment where you just get it. I really want to know how much they curve the test.
I do too.
Like, I really want to know.
Are you staying in here? Not I've been going back there probably. But I think other people are sitting.
Oh, you guys. Did you guys want to do the new subscription? T minus.
But I think are you coming back with us, Stacey? Yes, I am. Okay.
You have an hour.
We have a Stacey's coming. But I think hurry up.